Hello, my name is Javier David H. Bolong, and for this video I will be introducing the concept of fractals and the characteristics that determine what a fractal is.
But what are fractals? Coming from the word fractus, which means broken or shattered, it was a concept thought of by Benoit Mandelbrot. They are repeating patterns or formulae that can be found in the entire shape as well as its individual parts. Even as you look closer and closer on one spot, the pattern still repeats itself. In mathematics, this is termed as self-similarity. Before it was properly formulated by mathematicians, fractal-like shapes can be seen in nature, like in plants, organs, or in the cosmos. However, true fractals don't exist, due to cells and molecules existing. The pattern can only repeat to a certain extent before the structure of the cell and or molecules pops up. In fractals, certain fractals have their own characteristics. Certain fractals can have an infinite long perimeter while only having a finite space. For example, in the coastline paradox, which was observed by Louis Fry Richardson, he tried to measure the perimeter of Britain's coastline. He eventually reached a roadblock because landscapes have natural curves, edges, etc. that make it hard to get an accurate reading. To somewhat alleviate this and account for each and every rough edges, a smaller ruler would be needed. Each time the ruler got smaller, you'd need more and more rulers in order to measure the entire perimeter of the coastline. And each time, the length reading will be more accurate, but the value will get longer than before. You can repeat this process to account for each and every minute and minuscule roughness that there is in the coastline. And eventually, the length will just end up being infinite. Though the island of Britain was in a finite space, its perimeter had an infinite length due to roughness. And the same discovery can be applied to the Koch snowflake when it was discovered as a fractal. Another characteristic of a fractal is that it has fractional dimensions. When thinking of typical dimensions, we think of whole numbers like the first dimension, second dimension, third dimension, so on and so forth, wherein the first represents lines, the second represents shapes, and three-dimensional shapes as cubes, and so on and so forth. But given a line of length 2, we turn it into a two-dimensional object when we raise it to the power of 2, wherein it has an area of 4 square meters. To get a cube, you raise the length of the line to the power of 3, wherein it will have a volume of 8 cubic meters. But in a fractal like the Menger sponge, with the Menger sponge or cube, we are given a cube that has a length of say 3. Then we do the following formula. We subdivide the cube into 27 smaller cubes, and then we take out 7 of them, leaving holes. As you can see here, we take the middlemost cube that lays on each side and the one at the centermost of the cube. And then we repeat the process to the remaining smaller cubes. Each time a hole is made, a part of the volume of the cube is taken away. And do this long enough or slash infinite amount of times, there should be no more volume left from the cube. Yet, on the outside, it still looks like a three-dimensional shape. When doing the math during the first iteration, given the length of 3 on the cube side, and the remaining cubes left are 20, we are given the expression 3 is raised to d is equal to 20, where d refers to dimensions. And when we do simple iteration, in order to get the value of d, we get d is equal to 2.727. Although, and given this, the dimension of this cube is in between two-dimensional and three-dimensional, even though it looks from the outside as a three-dimensional shape. We already mentioned a few examples of fractals like the Menger sponge and the Koch snowflake. But the main body, we will discuss the more famous models like the Mandelbrot Set, Sierpinski Triangle and its variations, and we will see how fractals can be seen in real life and go more into depth into that and see how it's also applied to real life situations.
Hi, I'm Jed Fernandez, and I will be discussing Mandelbrot sets. Now we're going to be discussing Mandelbrot sets. The Mandelbrot set is a type of fractal first defined and drawn in 1978 by Robert W. Brooks. It originates in complex dynamics, and it can show how simple rules can produce infinite results. The Mandelbrot set is generated by iteration, which means to repeat a process over and over again. In mathematics, this process is most often the application of a mathematical function. In this case, we're going to be using a quadratic function. To iterate x squared plus c, we begin with the seed for the iteration. This is a number which you write as x sub 1. Applying the function x squared plus c to x sub 1 yields the new number x sub 2 is equal to x sub 1 squared plus c. Infinitely iterated, this produces a Mandelbrot set. Now we're going to be watching a visual representation of the Mandelbrot set in action. Here are some applications of the Mandelbrot set and where we can see them. Since a Mandelbrot set is a mathematical representation of fractal formation, these sets can be seen in various phenomena such as seashells, lightning formation, and snowflake formation. Mandelbrot sets can also be used in rendering videos, since it is very commonplace and it is easy replicatable.
Hello, my name is Alan Isabel and today I will be discussing what is Sierpinski Triangle, its application, and how to create it, as well as creating it in Python via codes. What is it? The Sierpinski Triangle is a self-similar fractal that contains equilateral triangle with smaller equilateral triangles recursively removed from its remaining area. It is created and named after the Polish mathematician named Wojciech Sierpinski. Now we go to the application of the Sierpinski Triangle. First application is just explaining the fundamental principle of fractals on how a pattern can repeat again and again at a different scales and how this complex shape can be made by simple repetition. The second application for the Sierpinski Triangle is for art. The Sierpinski Triangle hold a long history of being carved into walls of cathedral and even woven into the carpet for royalty. Even today, it is still being used by artists, as artists have described the incorporation of fractals in their art pieces as something chaotic yet having a defined form. Third use for the Sierpinski Triangle is for its uses for the multiband communication antenna. This is due to its intricate pattern that can be used to build and study antennas that can be used in any communication system with the requirement of a high bandwidth, different frequency band, and through all operating frequency, a constant radiation pattern. Lastly, it has a vital role as a defining property of Rule 90 in one-dimensional cell automation. In this case, in the space-time diagram of a Rule 90, which is shown in the right photo, when the beginning stage has a single zero cell, the diagram takes on the appearance of a Sierpinski gazette or a Sierpinski triangle. And due to the strong ties between the Sierpinski Triangle and Pascal Triangle, the Rule 90 space-time diagram also represents a module to Pascal Triangle. There are other forms for Sierpinski Triangle as well, and I would be showing you three of them. So first one is the cascading Sierpinski Triangle, which is just Sierpinski Triangle but shows a sequence shrinking in size. And the second one is the Sierpinski Parietal Triangle, but instead of using a equilateral triangle, it uses a acute triangle. And lastly is the Pascal Sierpinski Triangle. A Pascal Sierpinski Triangle incorporates the Pascal Triangle into the Sierpinski Triangle. This is done by coloring all the odd numbers in the Pascal triangle. The resulting shape from this step will result into the Sierpinski triangle. How to create the Sierpinski triangle? There are many ways to create a Sierpinski triangle, but one way is by the repeated removal of the triangular substance. This can be done in the following steps. First, take an equilateral triangle, divide it into 4 congruent smaller triangles, and remove the central triangle. Then repeat step 2 for each remaining smaller triangle forever. Here's a quick demonstration on how to create a Sierpinski triangle with the steps I mentioned before. So here we have a equilateral triangle with sides A, and we have to split it up into 4 smaller equilateral triangles. This can be easily done by locating the midpoint of each side and connecting them. So this is the midpoint here, midpoint, and then midpoint. And by connecting them up, this is the 4 congruent triangles, and now we just remove the central one. So there it is, and now we just repeat the steps for if you want to make it smaller and smaller. So like find the midpoint and make the 4 congruent triangles, and removing the middle one, and repeat. So there, another, and you can also do it here, and also here. And now removing it. And now we have our second. Then we just continue on. For the next part, the coding. So here we are in Jupyter Notebook, and I would be showing how to create a Sierpinski Triangle in Python. This is a really basic code that was inspired from Geeks, and it prints out the Sierpinski Triangle. So let's run it, and we'll see that the Sierpinski Triangle. We could also change how many. So like by changing number from the form of 2 to the n. So if you want a small one, you can say just 2. Just a small one. If you want to make it a bit bigger, so let's say 2 to the 5th, so 16. Then say it's a bit bigger. So it's just, this code is just basically knowing which, if it's gonna print a star or a space, depending on the which one is needed. So that's pretty much it for the code.
Okay, so hello, I am Cesar Agbayani Jr. I will be discussing the succeeding part of the discussion. Okay, so for the next part, I will give a general overview of the fractals, which includes the general applications and conclusion to sum up the discussion. Now, as we have seen already, fractals is very broad, a very broad concept. There is a lot to discuss in fractals in order to have a really clear understanding of the topic. But now we will turn in the general applications of the fractals, which is to say fractals in the real world. Fractals have a wide variety of applications ranging from programming to medicine and to nature even, due to its very systematic methods of capturing the roughness of some object. We will discuss these very applications in the following slides. Now, in medicine, fractals is very widely used. In fact, fractals are everywhere inside of us. Our kidneys, blood vessels, lungs, and brain all exhibit fractal formations. This very phenomenon, is why fractals are essential in the medical field. For example, healthy human blood vessel cells typically grow in a fractal pattern in nature, while cancerous cells, on the other hand, grow in abnormal fashion. This kind of distinction in between patterns makes it easier for experts to diagnose such diseases. Now, next we have urban planning. Cities are complex systems that bear similarities with that of a living organism in terms of behavior. When a city grows to a certain extent, which is when it absorbs its neighboring towns and villages, it develops a pattern in its structures that seem random at first, but resembles self-similarity on a larger scale. This kind of structure is said to be more efficient than modern urban planning, which are non-fractal in general. In general, an art is considered a fractal when a geometric design is created through continuously repeating mathematical pattern. In modern times, it is a form of algorithmic art generated through calculating fractal objects and representing the calculation results. The Mandelbrot Set, in particular, when created, generates different scenes based on the color scheme used for its display. Perhaps the most common application of fractals in the physical world is the trees. Trees are fractals in nature. On a small scale, the branch of a tree is a copy of the one that came before it, and on a larger scale, trees create patterns that repeat smaller and smaller copies of themselves to create the biodiversity seen in a forest. Now, in conclusion, fractals are geometrical figures that have identical repeating patterns on a scale that reduces infinitely. Though fractals are known for its similarity in nature, in general, a shape does not have to be exactly identical to be considered as fractal. A shape's inherent properties and repeating pattern similarities is instead examined to classify a shape as a fractal. The Mandelbrot set, a class of fractal sets in the complex plane, is an excellent tool for creating sample coastlines and landscapes in multiple resolutions that can be for testing other applications. Next, the Sierpinski Triangle, a shape consisting of an equilateral triangle with smaller equilateral triangles recursively removed from its remaining area, illustrates the fundamental principles of fractals, how a pattern can repeat again and again at different scales, and how this complex shape can be formed by simple repetition. So that will be all. Thank you for listening.